welcome to Same Day, Different Century. I'm Zach. Today is July 5th. On this date in 1686, Samuel Pepys, the same Samuel Pepys who kept one of the most celebrated personal diaries in the English history, put his name to a document in his role as president of the Royal Society. What he signed was an imprimatur, an official authorization to print, and what he was authorizing would become widely regarded as one of the most consequential scientific publications ever written, Isaac Newton's Mathematical Principles of Natural Philosophy. The printed book wouldn't reach readers until 1687, but that signature on July 5th, 1686, was the official starting gun on a work that would reshape civilization's understanding of motion, gravity, and the cosmos. A work so mathematically dense that even highly educated readers of its era struggled to follow the arguments, and yet a work whose conclusions provided the mathematical framework for physics, engineering, and much of natural philosophy for more than 2 centuries. By the 1680s, European natural philosophy had accumulated an enormous amount of solid data and useful theory, none of which fit together into a single coherent picture. Copernicus had proposed the heliocentric model. Kepler had shown that planetary orbits were ellipses and worked out precise mathematical relationships governing how fast planets moved and how long their orbits took. Galileo had studied inertia and falling bodies. All of this was real, hard-won knowledge, but there was a gaping hole at the center of it. Nobody could explain why planets moved the way they did. What force governed their motion? The dominant theoretical framework was René Descartes' vortex model, the idea that planets were carried along by vast invisible whirlpools of fluid spinning through the cosmos. But it was ultimately more metaphor than mathematics, and it couldn't fully account for what astronomers actually observed. Isaac Newton already possessed many of the key ideas, he just hadn't told anyone. During the Great Plague of 1665 and 1666, Cambridge University closed and sent its students home. Newton, then in his early 20s, retreated to his family estate at Woolsthorpe Manor in Lincolnshire. There, Newton developed the foundations of calculus, made key breakthroughs in optics and the nature of light, and began developing a mathematical theory of gravity. The famous apple story, a falling apple triggering a sudden revelation, is something Newton offered different versions of late in his own life. Historians treat it as origin myth, a tidy narrative that papers over what was actually a long, difficult, iterative process of calculation and revision. He was averse to controversy. An early paper on optics had drawn fierce public criticism, including from Robert Hooke at the Royal Society, and Newton had resolved afterward that he would publish only when he was entirely certain of his results, sometimes not even then. The world might have waited indefinitely for what Newton had worked out. What broke the deadlock was a visit from a 27-year-old astronomer named Edmund Halley. In August of 1684, Halley traveled to Cambridge specifically to put a question to Newton. Halley and 2 colleagues, the architect Christopher Wren and Robert Hooke, had been debating among themselves. If the sun's gravitational pull on a planet weakened with the square of the distance, what shape would the planet's orbit be? Hooke had claimed he had already proven the answer but had so far produced nothing. So Halley went directly to Newton. Newton answered immediately. The orbit would be an ellipse. Halley asked how he knew. Newton said he had already calculated it years before, but couldn't locate his papers. He would redo the work and send it along. What arrived a few months later in November 1684 was a paper titled On the Motion of Bodies in Orbit. Halley read it and quickly realized that he was not holding the answer to one question. He was holding the foundation of an entirely new physics. Not just an explanation for elliptical orbits, but a framework that could, in principle, account for the motion of every object in the universe. He returned to Newton and pressed him to expand this into a complete book. Newton agreed, and over the next 2 years, working in a state of concentrated focus that consumed him nearly to the exclusion of everything else, he produced the Principia. Then came 2 near-fatal complications. The first was Robert Hooke. When Newton's manuscript was presented to the Royal Society in April 1686, Hooke immediately raised a priority dispute. He claimed he had communicated the key insight of an inverse square law to Newton years earlier and deserved formal acknowledgement, perhaps even primary credit. Newton's reaction was volcanic. He threatened to withdraw Book 3 from the manuscript entirely. Book 3, which Newton titled The System of the World, was the section that applied all the abstract mathematics to actual astronomy, planetary motion, comets, and ocean tides. It was the payoff of the entire work. Without it, the book was a theoretical engine with nothing to drive. Halley spent weeks carefully managing Newton, reassuring him, appealing to his legacy, and convincing him to keep Book 3 in the volume. Newton ultimately relented. Most references to Hooke were quietly removed from the final text. The second problem was money. The Royal Society had agreed in principle to publish the Principia, but they had recently depleted their finances on a lavish illustrated natural history, a comprehensive study of fish that cost far more than anticipated and had left them unable to take on another major publication. Faced with this, Edmund Halley did something remarkable. He personally funded the printing of the Principia. He also proofread the manuscript, handled the correspondence with Newton through round after round of revisions, and contributed a laudatory Latin ode honoring Newton that appeared in the book's front matter. Halley's name is not on the cover, but without Edmund Halley, the Principia as we know it does not exist. Pepys signed the imprimatur on July 5, 1686. The printed books were in readers' hands by the summer of 1687. The Principia opens with Newton's 3 laws of motion. First, an object at rest remains at rest, and an object in motion continues in motion at constant speed in a straight line, unless acted upon by an external force. Second, the change in an object's quantity of motion, what we now call momentum, mass times velocity, is proportional to the force impressed and takes place along the straight line in which that force acts. Third, for every action, there is an equal and opposite reaction. These laws are the complete foundation of classical mechanics, and they were not obvious, not to the ancient world, not to the medieval world, and not even to most natural philosophers working in the decades before Newton. Every machine, every bridge, and every projectile ever calculated in the following 2 centuries would be analyzed using these principles. Then came the law of universal gravitation. Every particle of matter in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them, not just on Earth, not just in our solar system, universally, always, and everywhere. For the first time in history, one mathematical framework governed both a stone falling from a tower in Cambridge and a planet completing its orbit around the Sun. Newton used his framework to derive Kepler's laws of planetary motion from first principles, proving them mathematically rather than just observing them empirically. He calculated the behavior of comets, including one that Halley would later determine was a single recurring object, returning approximately every 75 years. He explained the ocean tides as the gravitational effect of the moon and sun pulling on the Earth's water. He predicted that the Earth itself must bulge slightly at the equator due to its rotation, a claim that was confirmed by precise geodetic measurements in the 1730s and 1740s. The impact of the Principia unfolded across generations. Astronomers eventually detected tiny irregularities in the observed orbit of Uranus that drifted from predicted paths. Mathematicians then used Newton's framework to calculate exactly where an unseen, more distant planet had to be to cause those deviations. Astronomers pointed their telescopes near that location and found Neptune within about a degree of the prediction. The Principia became one of the intellectual foundations of the Enlightenment. Thinkers across Europe saw in Newton's achievement something that went beyond physics, proof that the universe operated on rational, discoverable laws, that human reason, applied with sufficient rigor, could decode the mechanics of creation itself. This was a philosophical revolution with consequences in political thought and theology that extended far beyond anything Newton himself likely intended. Newton's mechanics stood essentially unchallenged for over 200 years, until Albert Einstein revealed that Newtonian mechanics are an approximation that falls under extreme conditions, such as very high velocities and in very intense gravitational fields. But Einstein did not erase Newton, he extended him. Today, NASA engineers use Newtonian mechanics to plot spacecraft trajectories through virtually the entire solar system, because within those parameters, Newton's framework is accurate enough that the relativistic corrections are negligible. Robert Hooke died in March of 1703. That same year, Newton was elected president of the Royal Society, a position he held for the rest of his life. The first edition of the Principia had a small print run, and copies became scarce almost immediately. Newton oversaw two further revised editions during his lifetime in 1713 and 1726. He died in 1727 at the age of 84. Within Newton's own lifetime, the Principia had already achieved something close to mythological status. Unlike most myths, the reputation was warranted. On July 5, 1686, Samuel Pepys signed his name to a piece of paper. By 1687, the book was printed and circulating, and the universe, as far as human understanding was concerned, was never the same again. That same day, different century. I'm Zach. We'll be back tomorrow with another date, another story. Thanks for listening. Hey guys, it's Zach. Real quick before you go, I just wanted to say thank you so much for listening. It really means a lot. If you enjoyed the show, all I ask is that you share it with someone that you think would enjoy it too. That's the best way to help us out. I'll see you tomorrow.